And what is ordinal logistic regression. So here is the data set. So let me explain you what the problem is. So I've taken a data set that has the rating of different cricket players, and there are various categories of cricket players we have taken into consideration. The problem that is given to us is that to find out the probabilities of a certain player getting a certain rating. Okay, and there are 9 categories of rating. You can see there are 9 ratings from rating 1 to rating 9, rating 9 being the highest rating and rating 1 being the lowest rating. And we have categories, so different categories of cricket players, and I'll explain what these categories are. Okay, so the first category is the Indian international, so Indian cricket players who is part of international team. Then foreign national, because in Indian Premier League there are also foreign players who are also participating. So foreign cricketers who are also playing international cricket are in the second category. Then the Indian domestic, so players who are playing in the domestic league, and they are from India, third category. And then foreign domestic. So these are the 4 categories. So we need to know, based on these categories, who's the likelihood of someone getting a particular rating. And there is also frequency, like from how many players we have found out this rating. So rating is the target variable for us, and category is going to be the independent variable, which is. And familiar with logistic regression, you know that it's a type of regression used to model categorical data. So if a target variable is categorical in nature, it has dichotomous, that means it has got 2 values. Most of the times it's 0 or 1, and they're trying to find out the probability of your target variable taking 1 or 0. So that's where you use logistic regression. Now, ordered logistic regression is an extension of logistic regression to multiple categories. So not just 2 categories, or not just dichotomous. You can have multiple values for the target variable. But you can have these ascending order or descending order. For instance, rating of players from 1 to 9 are in the ascending order. That means rating 1 is the lowest rating, and you can go up 1 to 2, and that's higher rating, and then 3 much higher rating, and up to 9. So they can be ordered. So rating can be ordered. So a case is where you have more than 2 categories. So here we have 9 categories, 9 types of rating, and they can be ordered. In that case, or in those scenarios, you can use ordinary logistic regression. So I'll just repeat. The target variable should have more than 2 categories, and the categories should be in ascending order or in descending order. It should be in some order. Okay, you can have an ascending order, descending order. In such a scenario, you can use ordinal logistic regression. Now, one of the assumptions of ordinal logistic regression is that there is assumption of proportional odds. Okay, I'm not going to get into the details of what proportional odds are, but from a prediction point of view, that assumption is not that relevant. But if you want to explain, if you understand how your independent variable affects your dependent variable, then that assumption is quite important. And okay, I'm going to build the model. So I have shown you the data. So we have got this as the dependent variable rating, and categories as the independent variable. The syntax is similar to what we have seen in the logistic regression. Proc logistic data, and then I'm going to use the data set players. That's the name of the data set, and we have class information. So category is it's a class variable, so we'll have these classes, and the reference category is 4. I'll explain what reference category is. That means when you will have the result, all the rest of the categories will be compared to the 4th category. So 4th category is nothing but the foreign players, right? Foreign cricketers, foreign domestic cricketers. So they are going to be compared with all other categories. Model is y is nothing but your rating. and then cat is the category. Okay, that's the only independent variables. Okay, so we'll run this, and I've already run this. I'll straight away go to the results. So let me show you how to interpret the results in a ordinary logistic regression. Okay, so you have 36 observation, out of which 28 have been used. So 8 observation have been removed. They may be having missing values, so that could be the case. So there are 9 categories in all. Okay, so total frequency, that means frequency will be used as a count. So frequency will be multiplied to the number of times it appears in the data set, and that's why it is total frequency, and that's the numbers. And then we need to see whether the convergence criteria has been met and it's satisfied, so we can be sure that the result is good enough to interpret. Otherwise, if this would not have been satisfied, then we cannot go ahead in understanding or interpreting the result. Alright, so we also need to look at the global null hypothesis state. It has to be significant, otherwise you cannot explain or you can interpret the result. So this has to be significant. So all the p-values are with the given less than 0.05, so it's significant. So okay, now we will go to the analysis of maximum likelihood estimation. So ordinary logistic regression, much like other logistic regression, uses a maximum likelihood estimation procedure to get the parameters. We have got several intercepts. Why? Because we have got several categories, right? So for categories, we have the estimates, the beta estimates, and the corresponding p-values. Now all are significant, as can be seen here, less than 0.05 in all cases. Okay, so what's important here is to understand what's the odd of somebody getting a lower rating and higher rating. So the idea is to understand somebody belonging to a particular category. Let's say somebody is from a foreign domestic player, how his chances of getting a lower rating is compared to someone playing someone from Indian domestic. This comparison. So category 1 to category 4, that means Indian international player has been compared to foreign domestic player. Okay, so the odds of Indian international player getting a lower rating compared to the foreign domestic player is 5.05. Similarly, the odds of the foreign international player getting a lower rating compared to a foreign domestic player is 143. Somewhat okay, and then category 3 compared to category 4, that means an Indian domestic player getting a lower rating compared to a foreign domestic player is 27.734. Okay, and then the C statistic is 0.789. The better the C statistic, the better is the model. So it normally lies between 0.5 to 1. The closer it is to 1, the better is the model. You can also look at all the comparisons. We look at, as I've said, 4 is the reference category, and in fact you can change the reference category. If you see the code, we have used the reference category this as 4. We can have the other categories as the reference category as well. So okay, so we can see the all the combination of categories. So cat 1 to cat 2, cat 1 to cat 3, cat 1 to cat 4, cat 2 to cat 3, cat 2 4, and then cat 3 to cat 4. So all the odd ratios have been estimated, and we have also the confidence limit for the odd ratios. Okay, so odd ratio gives an idea about, so somebody belonging to category 1, what is the likelihood that what the odds are in terms of getting a lower rating. Okay, so that's the idea here. So it helps us trying to understand, it actually helps, what's the real world uses of this. Well, the real world uses could be auctioning, like in Indian Premier League, while the franchises select players. So somebody, the chances or the odds of someone becoming a good player from a given category is what, that's the way they will price different players, and this is one way of doing that. Of course there could be many other factors will play, not just one factor. So the idea here is to understand how it works, and we can include more factors. It's not just categories that matters. In fact, there are other factors like player score, then his his run rate, his strike rate, his average, and so on. So many things um, matter a lot for factors. Finally, we can visualize the probabilities values. So somebody getting a lower rating because of belonging to a given category. Okay, so there are how many categories we have in place? Okay, so how come we have 9 categories? Okay, so this is rating, sorry. So categories are the 4 categories, 1 2 3 4, and 9 ratings, right? In the first category you can see 1 2 3. So which one are the highest, most rating? I think it is 7, 7 8 and 9. So 7 8 and 9 are the are the ratings mostly given to the category 1 players. Okay, and they're good rate, they're getting good rating, right? Similarly, you can see that for category 2 they're getting 5 6 7 8. 5 6 7 8 are the most category. Just look at the colors and compare here, and you will get to know that. Similarly, for category 3, you are mostly getting 4 5 6, yeah, 4 5 6, and for category 4 you are mostly getting 2 3 4 5. Okay, something like that. Okay, so you can see, you can compare the odds by looking at this visual plots, and it's much more clear. Okay, so once you have this model in place, you can also individually score each players and find out the probability of someone belonging to a given uh, rating, or somebody getting a rating, given rating. That also can be done. So we can use a score keyword and get the values. Okay. So that's basically the idea of ordinal logistic regression, wherein we are using multiple category instead of just 2 categories in a normal logistic regression to find out the probability and to find out the odds, or the odd ratio rather. So you how to build a logistic regression using stepwise variable selection methodology. So we'll take a data set. So here is a data set which is the details of cancer patients, and they have undergone medications, and we need to predict what is the probability that somebody has been uh, completely free of cancer. Okay, and in medical terms we call that as complete remission. So if somebody is completely free of cancer, then we assign a value of 1, otherwise 0. Whether somebody is completely free of cancer depends on the 6 variables. Okay, and we'll build a model, a logistic regression model to find out what is the probability that a patient is free of cancer. Okay, so to do so, and you have seen in the data set that the variable of interest has value of 1 and 0. So in such a case, when we have only 2 values in the target variable, we cannot use a linear regression. We have to use a logistic regression or a probit regression. So we'll go ahead with a logistic regression. Okay, so in SAS we use the procedure logistic, and the syntax is pretty simple. I'll explain it to you. Proc logistic data, and then cancer, which is the name of the data set, and then we're going to get our statistics, model statistics, in a in a data set, and that's why we're saving it as, we're calling it as betas. And then we'll define the model as this model, and the target variable is remis. We'll write that in the left hand side, and then we put all the factors as the independent variables in the right hand side. Now here uh, proc logistics, by default it considers the lower value as the variable of, or the value of interest, but we are not interested to find out whether somebody has cancer. We rather are interested in somebody is free of cancer after medication. So we're interested is in predicting 1, not 0. So we have to mention this explicitly. Okay. Alright, so this is the basic syntax of logistic regression, and then we'll come to the stepwise. So I'll start with the basic syntax, basic logistic regression. So I'll remove the selection part, and then we'll run this first, and then we'll go over to selection. So this is the plain vanilla form of logistic regression, which has got only the model and no variable selection or no feature selection in place. Okay, so let's run this. So how do we interpret the results? So you can see in the result, the first thing we need to see is that whether it has converged or not. Okay, so we need to see the convergence status first, and here you can see the model convergence status, and you can see that the convergence status or criteria has been satisfied. That means the result that is going to be followed is likely to be correct. Okay, if that's not satisfied, then you cannot explain the results that is going to come out of this estimation process. Okay, so there are few important statistics which are of interest to us. Model fit statistics, which is AIC, archaic information criteria, squash Bayesian criteria. Now these statistics are used to compare models. When you have similar models, a few of models, so the values AIC and SC are compared to see which one is the best model. Okay, since this is a single model, we won't get into the details of it, but while comparing we will make use of these values. Okay, and then testing for global null hypothesis. So the global null hypothesis says that whether your independent variables or the features, the 6 features that you have given as the input, are contributing towards finding out the probability of someone completely free of cancer or not. Okay, so global null hypothesis has the importance that if this is not satisfied, there's no point in going down and explaining things, and this seems to be satisfied because you can see that it is significant enough, so it's satisfied in this case. That means we are good to go with explaining our model results. The next in the result section is the analysis of maximum likelihood estimates. So logistic regression uses maximum likelihood estimation process to get the estimates, the point estimates. Okay, so, or rather we call that as beta parameters. We have the intercept and the slope, right? So we have got 6 independent variables, and we have also got an intercept. Okay, so there are 7 parameters we have from the estimation process. So all you need to see is how many of these parameters are significant. So how do we check that? Well, we need to look at the p-values. If the p-value is less than 0.05, then we are sure that the variable is significant at 95% confidence. You can see only one value is significant, right? Or not even that. It seems that all the independent value seems to be not significant. Okay, and that's quite strange, right? And it happens because we have very least number of observation. We have only 27 observation which we have given. So if we find any kind of issue with this data, we might have some strange result. And this looks quite strange because uh, none of the independent variables are significant. Okay, now we'll do an investigation into this. So before that, among the other thing that's important to us is looking at whether what to what extent um, the model is doing good job. So for that we need to look at what is known as the C statistics, or we call that as concurrence statistics. So C statistics lies between 0 to 1, and it has to be always greater than zero point 0.5. Otherwise there's no point in building a logistic regression model. Okay, so it most of the times is lies between zero point 0.5 to 1, and the closer it is to 1 the better is the model, and we have got a value of 0.88. That doesn't mean much, but we need that value to compare a model. Okay, so we will have several models in place through various techniques, and concurrence statistic is going to be useful while selecting the best model. Okay, so the one that we have seen is the basic form of logistic regression model, and what we have seen here is that there is some issue with this model because none of the independent variables are coming out to be significant. Okay, now oftentimes what happens is that some of the independent variables are not very important. In fact, they cause issues in the model. They cause the good variables. Some of the not so important variable cause the important variables to be not significant. Okay, so they affect the model adversely by making the good variable or the important variable insignificant. Okay, that we need to tackle. So we need to remove this unwanted variable or insignificant variables or not so good variables. So how do we do that? There are several selection techniques available. The popular ones are stepwise selection and forward selection, backward selection, and there is also another thing which is called subset selection, which we're not going to talk about it here, but we'll give a brief idea what subset selection is. Okay, so we'll use the first selection method that we're going to use is stepwise. So the same syntax except the fact that we're using a keyword selection, and then we are using stepwise as the selection method. Okay, so stepwise will remove some of the unwanted or unimportant variables from the model while estimating. So we'll have only the most important variables, and we hope that is going to improve the model. We have a few more syntax. Okay, two important keywords to remember is to have control over which variable is to be included in the model and which variable is to be not included in the model. If you don't use these two keywords and use that as part of your code, it is going to use the default values. Okay, default entry criteria and stay criteria. But if you want to have control over it, you can point. So what these values are: SL entry. SL entry is like what is should be the cutoff value for which would be used for an independent variable to enter into the model. And once it has entered into the model, um, so what is the criteria to keep it in the model? Okay, so these two are important to select a particular variable whether to be there in the model finally or not. Now why this question comes is because in stepwise regression equation you take stepwise approach. You do not build a logistic regression at once, just like we have done in the first case. We rather will have several such logistic regression with different set of independent variables. We'll see that in the result. So we'll first run this one. Okay, now that we have the result in front of us, so I'll straight away explain how the stepwise selection procedure works. Now, I have already said that there are several steps involved. In the first step, we do not have any variables. So the logic behind stepwise regression is that it is going to start with 0 variables, then it will add the most important variables and see if it is significant, and if it meets the selection criteria. If it meets the selection criteria, it stays, and the next important variable gets added to the equation, and then there is going to be another estimation, and then it will continue till the time we'll have all the important variables are in the model. Okay, now there are few cache. The first thing is that the entry criteria that we have mentioned should be satisfied. Okay, so it starts with step 0. It only has the intercept. So when we have intercept, it's nothing but the mean of the target variable. Okay, then in the next step, okay, the first variable li is now considered to be the most important variable out of the 6 variables. Now it enters the model. Now once it enters the model, because it has satisfied the criteria, it also stays with the model. That's what we have seen, because it is significant, right? It's less than 0.05, and it also meets the criteria for staying in the model. Now this is the criteria to stay in the model. Now internally it calculates the value, and it has found out that the p-value has to be less than 0.35 to stay in the model. Okay, and the p-value has to be less than 0.3 to enter into the model. Now both criteria have been satisfied, and this particular variable stays in the model. Okay, the second step, okay, in the step 2, so the next most important variable will be included. Okay, uh, so which variable has been included now? So we have temp. So the second important variable is temp, which is now part of the model, and it seems to be not so significant, but we'll see whether it actually is the criteria of staying in the model is satisfied or not. It could be satisfied, so internally it evaluates, and there seems to be no effect. That means it doesn't drop out. If it doesn't satisfy that, it will drop out of the model, right? It might drop out, but it seems no effect in the model in steps 2. That means the 2 important variables that we have included so far they stay within the model, and none of them drop out, because the stay criteria has been met. From the model, it stays in the model. Okay, and the final message that no effect made for 0.3 significant level for entry into the model. Apart from these 3 important variables that entered and stayed in the model, no other variable, the last 3 variables, did not meet the entry criteria. So a variable which did not meet the entry criteria will not be checked for stay criteria, because it doesn't enter also. Only when the variable enters the model, it will be checked whether it it satisfies the stay criteria. Only if it satisfies the stay criteria, it stays in the model. Otherwise, there's no point in including these variables in the first place. So the message is clear: no additional effect made the 0.3 significant level for entry into the model. Alright, so we have finally 3 very important variables, and alright, so now we have the variables and the significance level. You can see one variable is significant, the other 2 are not so significant, but given that we have small data, we have been um, slightly liberal in terms of keeping the variable at even lower significance level. Okay, so first one is very significant, the other 2 are not very significant, but they actually help you they help in predicting the target variable, so is important. So let's see what the concordance statistic is. So the C statistic is 0.889, which is slightly improvement from what we have seen in the plain vanilla, the first model that we built. Okay, so that's about stepwise regression model. Now the good thing that has happened is that, so in a first case there was not even a single variable which was significant. Now we have at least one variable which is clearly significant, and the two variables which are not significant yet they're contributing towards predicting the target value. Okay, now we can also see other selection techniques such as backward selection and forward selection. I'll briefly talk about these two techniques. Okay, so the syntax remains same except the fact that in the selection I have used backward instead of stepwise as we have done in the previous one. Alright, so in backward technique what happens is that you start with all 6 variables and then you keep on dropping till the time your entry criteria or exit criteria is not. So we haven't mentioned any entry or exit criteria, so it is going to take the default one. Okay, so we started with variables, independent variables, and we'll see in what. Okay, so in the first step, this variable blast is now removed from the, because it doesn't meet the stay criteria here, right? It starts with all variables. In stepwise we started with no variable and then it entered, and it could drop at any time also. In backward it starts with all variables and it slowly drops the unimportant variables. The first step, blast, gets dropped. In the second step, this variable infill got dropped. In the third step, smear got dropped, and finally I think everything else met, and the 0.35 significance level has been used while dropping them. So the stay criteria has not been made for three important variables, sorry, unimportant variable, which have been dropped out from model. Now finally you will have your estimates as this, and you can see here also we have one significant variable and two nearly significant variable. Okay, and also need to look at the C statistics, which is same as what we had got in this stepwise regression. So finally we'll see the forward selection criteria. Well, in forward selection criteria, it's exactly the opposite of backward selection criteria. So it starts with no variable, okay, and keeps on adding. But you might wonder, how is it different from stepwise, because stepwise also does the same. Well, in forward selection, if a variable is part of the model, or it has been entered into the model, it will never drop off. Whereas in stepwise it can drop off at any step. Okay, so if a variable x has entered into the model, it can, in the first step, in the second step it might drop off, because in the presence of second variable it might not be significant, it might drop off. But in forward, once something is part of model, it is never going to drop off from the model. It is going to be there in the final model as well. So in the 3 steps, I think here also there are 3 steps, and in each step the most important variable in the order of importance gets added to the model, and I'm sure 0.3 significance level has been used to, so in backward we have only the stay criteria, the significance level for stay criteria. In forward we have significance level for entry criteria. In stepwise you have significance level both for entry as well as for stay. So stepwise is a combination of, it combines the forward and backward, and that's why it's considered better than both these two selection techniques. And as we can see, the result is more or less same, except the fact that there is slight, I rather say it's same. So so in such a case, when we have only 6 variables and 30 observation, there won't be much of a change. But if you have large set of observation, and if you see a large set of variables and you use these selection techniques, you will see a significant difference in terms of finding the most significant variables or the best set of variables, and um, also in the concordance statistics, which is going to give you an idea of how efficient your model is. And how do we select? Yes, so the important is, given the fact that we have now many selection techniques, which selection technique is to be finally used? Well, the one that is to be used should have the highest predictive ability, and that would be that you can find out by looking at the C statistics. The one that has the highest C statistics, go ahead with that. And if you have similar C statistics, look at the AIC and SC values. AIC and SC, right? That's what we have shown in this case. If you go on the top, you have AIC and SC, right? So okay, somewhere down you have AIC. Okay, here. So look at the AIC values and compare. The one that has the lowest is the one. So start with C statistics, compare. The one that has highest should be taken, and there is no question. If they're all same, then go to the AIC and SC criterion, and the one that has the lowest AIC should be used as the final model. Now finally, given the fact that stepwise regression does a good job, we'll go ahead with stepwise. And what we have done here is that we're also predicting a value, or technically we're calling that as scoring a value. So we have a model which has got three important variables in the model. So using the statistics, the beta parameters, we will score the model. So what do we get in the score? We get the probability of someone having cancer or not, right? So that's the main output we're interested in, and that will have in the data set PRED. Okay, so here against each individual patient, you have a probability value which lies between 0 and 1 of somebody completely free of cancer or not. The first candidate 0.72. So it's saying that it's likely that the candidate is free of cancer, and the actual value is 1, so that matches, that's a correct prediction. Second, it's 0.57 and it's also 1, so cutoff value that we normally take is 0.5. That means anything above 0.5 probability is considered that it is giving a value of 1. So the actual value is 1 and the predicted value is 1, so it's a correct prediction. So you look at these values and see how many times you have got correct prediction. Okay, that will give you confidence before you can use this model in the production. That means you can use this model to score new patients, to know whether someone is completely free of cancer or not. There's also a lower limit, confidence limit, and a higher confidence limit for each one of these predicted values, so that it gives you an idea what is the bracket, or what is the lower limit and upper limit of this probability value. But what's most important is this one. Okay, so we have been able to score this. Now this can well be used for new data also. Like for this data we already have the target variable, but for the new data we may not have the target variables. So by looking at this probability values and taking 0.5 as the cutoff, we can find out whether somebody is free of cancer or not. So that's a small example to understand the stepwise logistic regression, and how stepwise logistic regression is different from forward logistic regression and backward logistic regression. Thank you.